Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the godlike genius that can't count. In this page, we will cover the strange paradox where modern large language models feel genuinely intelligent yet fail at the simplest tasks. We often see these systems effortlessly translate complex languages and write brilliant poetry that rivals human masters. However, if you ask this cosmic genius to count the number of letters in a simple word like strawberry, it often fails miserably. This raises a profound question for all of us studying artificial intelligence. Why does a system that is seemingly fluent in quantum physics and advanced philosophy struggle with the basic math you would find on a $5 calculator? This disconnect suggests that what we perceive as intelligence might be something very different under the hood. We are going to explore why these digital giants stumble on tiny stones even as they leap over mountains of data. It is a mystery that goes to the very heart of how these machines actually process information and why their genius has such specific and surprising limits. In our second page, we explore the cosmic guessing game to understand why AI fails at simple reasoning. It is important to realize that this paradox is not a software bug that can be easily patched. Instead, it is a structural reality of how these models are built. Deep learning models are essentially massive pattern matchers rather than logical reasoners. They do not possess a central database of facts or a set of rigid rules. Instead, they operate by simply predicting the most probable next word based on the patterns they have seen in their training data. We must understand that probability is not the same as truth. We have essentially built an incredibly articulate guessing machine that sounds very confident, but lacks an internal mechanism to verify facts. When a model predicts a word, it is doing so because that word is statistically likely to appear next, not because the model understands the underlying logic of the sentence. This creates a fascinating but dangerous illusion of intelligence where the machine can explain the stars, but cannot count its own fingers correctly. Understanding this distinction is the first step toward seeing the true nature of modern artificial intelligence. Welcome to page 3, where we meet the Vibe machine. This page focuses on connectionism, the branch of deep learning that attempts to mimic the biological structures of human brains. This approach is powerful because it finds probabilistic patterns in massive amounts of unstructured data. This is why AI excels at art, language, and creative tasks without requiring any human-coded rules. It learns the vibe of a style or a language through exposure. However, because it operates entirely on statistical vibes, it is prone to confidently hallucinating falsehoods. Since there are no hard rules to keep it grounded, the model can drift away from reality if the statistical path leads it there. It creates beautiful images and flows of text by following the flow of numbers, but it lacks the anchor of logic. This is why we see such amazing creativity paired with such baffling errors. The Vibe machine is excellent at capturing the essence of things, but it often misses the literal truth. It is like a dream that feels real but has no substance. As we move forward, we will see why this lack of internal logic is becoming a major hurdle for developers who want to use AI in more serious and sensitive applications. On page 4, we take a trip back in time to look at the medieval logic castle. For over 40 years, the field of artificial intelligence was ruled by what we call symbolic AI or good old-fashioned AI. This approach operates on hand-crafted explicit rules and flawless logic. Think of it as a rigid castle built of stone where every block is a rule. The pros of this system are significant because it is 100% reliable and fully auditable. Every decision the machine makes can be traced back to a specific mathematical proof or logical rule. However, the cons are equally significant. These systems are incredibly brittle. They fail entirely when they are faced with the unstructured and messy reality of the real world. If a situation does not perfectly match one of the predefined rules, the system has no idea what to do. While the Vibe machine we discussed earlier is too fluid, the logic castle is too rigid. This historical perspective helps us understand why the current boom in AI moved away from rules and toward patterns. But as we are now discovering, by throwing away the castle to embrace the vibes, we might have lost something essential for true reasoning and safety. In page 5, we discuss the idea that AI only has half a brain. To understand the current state of technology, we can look at how human intelligence works. According to psychological theories, human intelligence relies on two systems working together. System 1 is fast and intuitive, handling perception and pattern matching without much effort. System 2 is slow and deliberate, handling logic and explicit reasoning. Right now, our magical AI systems act almost entirely on instinct, which is the equivalent of System 1. They are brilliant at the fast and intuitive part, but they lack the capacity for the slow and steady deduction that defines System 2. They can recognize a face or finish a sentence in an instant, but they cannot sit down and work through a multi-step math problem with guaranteed accuracy. This imbalance is why AI feels so smart yet acts so dumb at the same time. We have essentially created a digital brain that is all intuition and no reflection. To reach the next level of artificial intelligence, we need to figure out how to give these models the other half of the brain. We need to find a way to integrate the slow logic of the past with the fast intuition of the present. Page 6 addresses a common misconception with the title, "A Faster Guessing Machine Cannot Think." Many people believe that if we just feed more data to these models, they will eventually become smarter and solve their logic problems. However, feeding more data to a flawed architecture does not solve its underlying logic deficit. When faced with strict deductive puzzles, even the largest models often blindly parrot text they have seen before rather than thinking through the problem. Scaling up an intuition engine simply yields a faster and more confident guesser, but it does not create a thinker. A great example is the riddle about feeding a wolf to a cabbage. Because the model has seen many variations of the classic river crossing puzzle, it might try to apply the old solution to a new version that does not make sense. It parrots the pattern rather than reasoning about the actual hunger of a wolf or the nature of a cabbage. This proves that size alone is not the answer. We cannot simply grow our way out of the reasoning gap. We need a fundamental change in how these systems are structured if we want them to do more than just guess. Real intelligence requires the ability to stop and check if the current path makes sense against the laws of logic. On page 7, we look at the high stakes of life or death in the black box. In fields like medicine and aviation, we cannot afford to have a system that just guesses. These areas require explainability and a clear trail of logic. Neural networks currently lack interpretability because they are black boxes where billions of numbers shift around in ways humans cannot easily follow. If an AI cannot trace its exact reasoning steps for a medical diagnosis or a flight path, it is simply too dangerous to deploy in the real world. This is not just a technical preference, but a legal requirement. The EU AI Act and other global regulators are now demanding explicit transparency from AI developers. They want to know why a machine made a certain decision. If the answer is just that the statistics favored that outcome, it is not good enough for a hospital or an airport. We need systems that can show their work just like a student in a math class. Without this ability to show logical work, the power of neural networks will remain limited to low-stakes tasks like writing emails or generating art. For the world to truly trust AI, the black box must be opened and filled with clear and understandable logic. Page 8 introduces the solution with the marriage of pattern and rule. The future of the industry is something called neurosymbolic AI. This approach involves combining the brilliant intuition of neural networks with the unbreakable old-school rules of symbolic AI. It is a way to get the best of both worlds. In this framework, the neural network acts as the visual cortex. It is responsible for looking at the messy and unstructured world and translating it into something understandable. Meanwhile, the symbolic engine acts as the prefrontal cortex. It takes the information from the neural network and performs flawless reasoning over symbols and rules. This creates a system that can both see the world and think about it logically. It can handle the nuance of human language while still adhering to the laws of mathematics and physics. This marriage represents the most promising path toward creating truly intelligent machines that are both flexible and reliable. By bringing the castle and the vibe machine together, we can build a structure that is both beautiful and strong. This is the core philosophy of the next generation of artificial intelligence development. In page 9, we look at paradigm 1, which is translating the chaos. This is the first way neurosymbolic systems work. Neural networks take the unstructured reality of our world, like a handwritten note with coffee stains, and translate it into clean and digital data. Once that data is cleaned and structured, the symbolic engine takes over. It processes that clean data with mathematical certainty. Each side does exactly what it is best at, which effectively bridges the gap between perception and logic. For example, a neural net might look at a messy equation written on a napkin and identify the numbers and symbols. Then, a symbolic math engine solves that equation perfectly every single time. The neural net handles the messy part of seeing the pixels, and the symbolic part handles the actual calculation. This division of labor ensures that the final output is 100% correct. It is like having a person who is great at reading messy handwriting and a person who is a world-class mathematician working together. This collaboration eliminates the errors that happen when a neural net tries to do math on its own. It provides a blueprint for how we can make AI systems that are both perceptive and perfectly accurate. Page 10 covers Paradigm 2, which involves giving AI a calculator. You have likely already used a primitive version of this tool use architecture if you use modern chatbots. When a large language model writes Python code to solve a math problem, it is performing a form of neurosymbolic reasoning. In this scenario, the neural network is used to understand your natural language request. It interprets what you want to achieve. However, it does not try to do the hard math itself. Instead, it hands the actual calculation off to a perfectly reliable symbolic interpreter, like a Python compiler. The Python environment doesn't guess. It follows strict rules to get the right answer. This approach allows the AI to stay within the realm of logic while still being easy for humans to talk to. It is the digital equivalent of giving a poet a calculator. The poet provides the creative direction, and the calculator provides the numerical accuracy. This is a very powerful way to overcome the limitations of pattern matching. By allowing the AI to use external tools that are based on hard logic, we can solve many of the counting and math problems that plague standard models. This paradigm is becoming standard in the industry to ensure that AI can be used for technical tasks. On page 11, we explore Paradigm 3, which is the ultimate truth checker. We can tether the language skills of an AI to a strictly verified and auditable knowledge graph. In this setup, the neural network handles the fluid conversation, ensuring that the interaction feels natural and human. However, the actual answers provided are strictly constrained by the knowledge graph. A knowledge graph is a database of facts and relationships that have been verified as true. If the graph says that two specific drugs cannot be mixed safely, no amount of statistical pressure from the neural net can override that rule. The system is literally chained to the truth. This prevents the model from hallucinating dangerous medical advice or incorrect legal facts. Even if the training data has conflicting information, the symbolic knowledge graph acts as the final authority. This is essential for building trust in enterprise and scientific applications. It ensures that the AI remains a helpful assistant while preventing it from making up its own version of reality. By combining the conversational power of LLMs with the factual rigidity of knowledge graphs, we create a tool that is both eloquent and truthful. It is the ultimate safeguard against the unpredictable nature of pure statistical models. Page 12 presents a real-world success story with winning the Math Olympiad. DeepMind created a system called AlphaGeometry that solved Olympiad-level math problems using a neurosymbolic system. This was a major milestone in the field. The neural model provided the intuitive ideas of where to draw complex geometric lines on a page. This is the creative part of solving geometry that is hard to code into rules. However, once those lines were proposed, a symbolic engine rigorously verified the logical proof step by step. It checked every angle and every line to make sure they followed the laws of geometry. By combining these two approaches, the system reached a level of performance that approached the exact score of human gold medalists. This proved that neurosymbolic AI is not just a theory. It is a practical way to achieve world-class performance in the most difficult reasoning tasks. It showed that when you give an intuition engine a logical partner, it can solve problems that were previously thought to be impossible for machines. This success has inspired a new wave of research into how we can apply these combined systems to other scientific fields that require both creativity and extreme logical precision. On page 13, we look at the vital task of saving the duck with hard logic. This page uses the example of autonomous vehicles to show why logic matters. Pure neural networks in self-driving cars can crash during weird edge cases that they haven't seen in their training data. If a car encounters a strange object it doesn't recognize, it might make a fatal guess. To prevent this, developers are layering symbolic safety constraints over the AI. These constraints essentially hardcode the laws of physics into the car's brain. For example, rule number 1 might be to never accelerate if an object is detected within 3 feet of the front of the vehicle. The AI can guess and predict patterns all it wants, but this hard rule saves the duck and the human in the real world. These rules act as a symbolic shield that the neural network cannot penetrate. Even if the AI thinks it sees a clear road, the safety rule will stop the car if the sensors detect an obstacle. This hybrid approach is the only way we can safely put AI in charge of multi-ton machines moving at high speeds. It ensures that even when the intuition of the AI fails, the logic of physics remains in control to prevent accidents. Page 14 is about reclaiming the past to build the future. To move forward in the field of artificial intelligence, we must be willing to look backward. For a while, we discarded strict human logic to build magical and data-driven black boxes. We were so impressed by the power of big data that we forgot the importance of reasoning. However, to achieve true artificial general intelligence, or AGI, we need more than just better patterns. We need explicit causal models that understand how the world works. We must invite the old pioneers of symbolic AI back to the table to help us build these new systems. The goal is to combine the deep history of logic research with the modern breakthroughs in neural networks. We are realizing that the path to a thinking machine is a loop that brings us back to the fundamental principles of logic and mathematics. By blending the old and the new, we can create a form of intelligence that is much greater than the sum of its parts. This is an exciting time for AI because we are finally seeing the full picture of what is required to build a mind. It is a journey that requires both the wisdom of the past and the technology of the future. Our final page is titled A True Mind for a Chaotic Cosmos. The universe we live in is messy and unpredictable, and we have built guessing machines that reflect that chaos. They are amazing tools, but they are incomplete. By weaving in human-made and rigid logic, we can finally tame the chaos of statistical models. We are no longer just building a statistical calculator that tries to guess the next word. Instead, we are building a reliable and truly intelligent companion for the deep future. This neurosymbolic approach gives us the best chance to create AI that understands the world as well as we do. It will be able to help us solve the greatest challenges of science, medicine, and engineering with a level of precision we have never seen before. We are moving toward a future where machines don't just mimic human speech, but actually share in the human capacity for reason and truth. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.